Okay, here we go. All right, so this is a pre-calculus video for 1.4, 1.5. That homework assignment is on WebAssign. Let's go ahead and get started. The learning targets, I'm gonna present my little thing here. Learning targets today are identifying the domain and range of a function, domain algebraically, and then domain and range using a graph. Evaluate functions, including piecewise functions. We're going to talk about functions, what functions are, that sort of thing. And then identify where functions are increasing, decreasing, and constant. And we're going to talk a little bit about relative maximum, relative minimum, and absolute max, absolute min, just a little bit. So a little bit of vocabulary, a little bit of math stuff, and probably quite a bit of me just talking and not writing stuff on the board. Because, well, I mean, if you really want to see it written, just turn on the subtitles, a closed caption. It's amazing. Like, you can do it in different languages, and it'll write it out for you. So, a function, remember, a function is a relation that assigns each element in the domain. Domain usually has x, so each x to one and only one element in the range. So each x gets exactly one y that it goes to. If we draw a graph, right? Remember, this is our x-axis, this is our y-axis. Write a graph like that, let's say, something like this. Every single x goes up to one and only one y value. Now, if we have something like this, let's say, there's an x value, let's say like 1, 2, 3, right here. When x is 3, there are 3 different outputs. So if there's 3 different outputs, that says, well, we don't know when x is 3 which answer is the correct answer, basically. So that does not represent a function. This would be a relation. It can still be like expressed using an equation. There might be like plus and minus, that sort of thing going on in there. There's 3 of them, so it'll be a tricky equation. But it's still a relation, but it's not a function. A function means every single x number has one and only one y number that it goes to, exactly 1. All right, so for a function, right, the domain is a set of all the inputs, all the x numbers that are possible. The range is a set of all the y numbers, or the set of all the outputs that are possible for the function. Independent variable is like all your independent number, independent variable, those are your x numbers. Dependent variable is usually your y's. Usually you've got something like this, like y equals like 5x plus 2. So here, or you could have f of x equals 5x plus 2, let's say. So basically the y or the function f, these can be interchangeable, but the output depends on what the x number is. So we call the x number this thing here, that's our independent variable, and the output is dependent. Depends on what comes out, or depends on what the x is. Function notation, this is function notation. We're going to be using this mostly in pre-calculus. So we're not going to be seeing that much of the y equals. It's mostly going to be f of x equals. You'll see a lot more f of x and g of x and h of x equals in calculus as well. Reasons for function notation, right, gives us more information. So if I write like f of 2 equals 12, that means if x is 2, then y is 12 versus y equals 12. Also, we can talk about different functions at the same time by saying like this is f of x, this is g of x, this is h of x. So we'll be using function notation quite a bit. Let's go ahead and jump into evaluating functions using function notation. So here's where we get to like a little bit of math stuff to it. So let's say we have g of x equals negative x squared plus 4x plus 1, and we want to evaluate g of 2, g of t plus g of 0, and then we want to evaluate g of x plus 2. All right, so these are 3 different problems, all based on the same g function. So to evaluate g of 2, what we do is we just go, instead of g of x, we have g of 2. So what we do is we replace every x with a 2. So we're going to go negative 2 squared plus 4 times 2 plus 1. And whenever you're doing this, it's usually best to, for whatever you are evaluating, whatever number or expression you're evaluating inside the function, just put parentheses around it everywhere there would be an x. So let's go ahead and simplify this. So negative 2 squared is 4, so we have negative 4, plus 2 times 4 is 8, plus 1. So here it's 9 minus 4 equals 5. So we would say g of 2 equals 5. Boom. Wonderful. All right, let's do another one. Let's do g of t plus g of 0. And notice I'm saying g of t when I write this, saying the function g evaluated at t. G of 0 means the function g evaluated at 0. So g of t is going to be the same as g of x, but instead of x's we have t's. So g of t is going to be negative t squared plus 4t, not 40, 4t plus 1. I just replaced the x's with t's, so that's g of t. And I'm going to go plus g of 0, which is negative 0 squared plus 4 times 0 plus 1. I'm going to simplify this. Here it's just negative t squared plus 4t. I've got plus 1, that's 0. This is all just 0, so I've got plus 1 plus 1. So it's plus 2. So this is g of t plus g of 0. Basically, g of 0 is just 1. So it's g of t plus 1. All right. And notice with this one, with the addition outside, so it's g of t and then plus g of 0, we evaluate this one, we evaluate this one, we combine them. That's different than this problem here where we have g of x plus 2 inside the parentheses. So this, we call this x plus 2, that's the argument of the function. X is the argument here, inside the argument of the function. So what we're doing is everywhere there's an x in the original g, we're going to replace it with an x plus 2. So we're going to go negative x plus 2 squared plus 4 times x plus 2 plus 1. Right? So this is this here, but instead of with an x, it's an x plus 2 everywhere for an x. So now we're just going to simplify. So we're going to say equals negative. I'm going to square this. I'm going to multiply it out. Remember, x plus 2 squared is x plus 2 times x plus 2. So we're going to get x squared plus 4x plus 4. Right? We do that by going, if you want to draw the box, x plus 2 times x plus 2. X squared, 2x, 2x, 4. Combine the two x's, that's where we get that 4x from. Right? And then I go plus. I'm going to distribute this 4x plus 8, and then plus 1. All right, still it's a negative out here, so I got to distribute, and then I can simplify or combine like terms. So we bring that negative in, we get negative x squared minus 4x minus 4, and then we have a plus 4x plus 8 plus 1. Combine all the like terms together, stay purple. We get a negative x squared. We've got a negative 4x and a positive 4x. Those are just going to cancel out to 0. And then here I've got a negative 4. And then the 8 plus 1, that's 9 minus 4 again, so it's a plus 5. So boom, g of x plus 2 is negative x squared plus 5. All right, so you should be able to do similar problems on the homework to this. Evaluating function, right? Replacing the x of the function with whatever's inside the parentheses. Even if it is a binomial or it could be a trinomial or whatever, use g of x plus 2. Everywhere there's an x, we put in an x plus 2 and then simplify. All right, so that's evaluating a regular function. Now we're going to move to piecewise functions. So piecewise functions look like this. So we can say f of x equals, and then there's a crazy fun bracket where it's 2x minus 5 for this one. When x is less than or equal to negative 2, it's x squared, there we go, plus 3x minus 1. When x is between negative 2 and 3, and it's 4x when x is greater than or equal to 3. I just made this function up. Piecewise functions are often used, like in real life or real applications. Like if something like with taxes, right? You've got a certain tax bracket until you hit a certain value, or like your wages go up to a certain amount, and then you go to another tax bracket. So that's an example of a piecewise function. Here, what this is saying is basically this function is if the inputs are negative 2 or lower, you use this part, this piece. If the inputs are between negative 2 and 3, you use this piece. And if the inputs are greater than or equal to 3, you go 4x, 4 times that input. So we're just going to evaluate a few of these. We're going to say f of negative 2. We're going to evaluate f of negative 1. And we're going to evaluate f of 4. Go ahead and pause the video and try to evaluate each of those and see what you get. So go ahead and pause it, try it, and then we'll go over it together. Well, I'll go over it and you'll watch, I guess, because you're not here, you're in front of the computer. Hopefully you paused it. Let's go over it. So f of negative 2, right? We're saying which negative 2 is the x number. Where does that land? It lands less than or equal to negative 2 because it's equal to negative 2. So we're going to use this 2x minus 5. So we're going to say 2 times negative 2 minus 5. We're using this function, or this piece of the piecewise function. So it's negative 4 minus 5, negative 9. So equals negative 9. Boop. Got it. Cool. Now let's look at f of negative 1. Negative 1 is between negative 2 and 3, that x number. This is x equals negative 1. It lies between those two. So we're going to use the quadratic part of this piecewise function. So I'm going to go negative 1 squared plus 3 times negative 1 minus 1. Negative 1 squared is negative 1 times negative 1. It's positive 1. And then minus 3 minus 1. And that gives us negative 3. So this equals negative 3. Lastly, f of 4, here x is equal to 4. 4 is greater than or equal to 3, so we use this part. So it's 4 times 4, which is 16. Right, so it depends which number is inside the parentheses for which piece you use. And sorry, I shouldn't have had these in the same order as those, my bad. But hopefully you get the idea that you're just looking, what's the x number, where does it lie, in which interval does it lie? If it's in this, if it's less than or equal to negative 2, use this part of the function. If it's between negative 2 and 3, use that one. If it's greater than or equal to 3, use that part. Okay. And once again, right, find me during my office hours if you have questions. I'm happy to help you. All right. We are going to jump to talking about the domain of a function, how to find that algebraically. All right. And remember, if I'm going too slow, there's always that speed it up button, right? And then you can slow it down button too, right? It's a little gear and it's a playback speed, so you can, you know, maybe talk like 1.25 speed instead of regular 1 speed. And hopefully you're taking notes on this as well, so you have those notes to use when you're doing your homework. All right, we've got 3 functions here. We have f of x equals 4x plus 6. We have g of x equals the square root of 4 minus 3x. And then we have h of x equals x plus 1 over x squared plus x minus 6. All right. And we want to know what's the domain of each function. What's the domain of each function. That's what we're trying to find here. Because the learning target is we'll find the domain of a function algebraically. So we look at it, and the domain is the set of all numbers that are defined for that function. And in general, unless we're stating otherwise, we're dealing with the real number system. So real numbers, not dealing with imaginary numbers or the imaginary parts of the complex numbers. Just the reals right now. We'll get into imaginary and like that whole complex field later. All right, so looking at the first function, f of x equals 4x plus 6. When you're trying to find the domain of a function, what you kind of want to be thinking is there any number I can put in for x that would kind of make things go wonky, just make it not work? So we think about it, we're like, well, what's happening to x? We're multiplying by 4. Is there any number I can't multiply by 4? I mean, 0, you multiply 0 by 4, positives. 4 times a positive just gets 4 times bigger. Negatives, right? 4 times any negative just makes it 4 times more negative, so that's fine. So any number works for x, for multiplying by 4. What about adding 6? Can we add 6 to any number? Yeah, it makes it 6 bigger. So here, any number I put in for x, I can multiply it by 4 and then add 6. It works. So the domain here, the domain of the function f is all real numbers. And that's what we're going to write, all real numbers, for the domain of f, for that function f of x, 4x plus 6, because you can put any number in for x and get an answer, you get a y number out. Right, if you look at the graph is a line. The line goes all the way in the negative direction, all the way in the positive direction. You get all of them. All right, let's look at g of x. G of x, we've got square root of 4 minus 3 times x. So we already talked about like this linear action here, right? 4x plus 6, we can do any number linear. So the 4 minus 3x is fine, it's linear. What about the square root? Are there any numbers that we cannot square root? In the reals, we're talking about real numbers, any numbers that we can't square root. And you should be thinking, yeah, we can't square root negatives and get real number answers. We can get complex numbers, it's fine. We're not doing that right now, we're just dealing with the reals. So here, if we're trying to find the domain of the function g of x equals square root of 4 minus 3x, we gotta make sure that we're only putting in x numbers that make us square root non-negative numbers. So here, what we do is we take what's inside the square root, the argument of the square root, which is 4 minus 3x, and we say that has to be 0 or positive, okay? Because we can square root 0 and we can square root positive numbers. So the way to mathematically say this thing under the square root is 0 or positive is we say it's greater than or equal to 0, right? And that's going to make sure that if I solve this for the x numbers, I'm getting all the x numbers that will give me the square root of a 0 or a positive number in there. As in, I'm not going to square root the negatives. So let's go ahead and solve it. We're going to go minus 4 minus 4. Remember, just undoing, we've got negative 3x is greater than or equal to negative 4. Divide by a negative 3. Should be a little alarm going off in your head, like, we divided by a negative. What happens when we are solving an inequality and we divide by a negative? Right, that inequality sign switches because, right, if you're talking about positive numbers, right, far away from 0 means bigger. If you're talking about negative numbers, far away from 0 means smaller. So whenever you multiply or divide by a negative, you're switching what side of 0 you're on, but you're still keeping that relative distance away from 0. So if you're positive, far away means big. If you're negative, far away means small. So whenever we switch sides, we got to switch what that inequality means. That's what's going on here. So here, this is saying x is less than or equal to 4/3. So those are all the x's. So now we're going to write the domain using what we call interval notation. So interval notation. So here, we've got all the x's that are less than or equal to 4/3. So we write 4/3 as our biggest one. and we put a bracket after it. The bracket means it can equal that. And then we want everything less than it, so we say it goes all the way to negative infinity, but we can't actually get to negative infinity because, well, infinity is not a number, it's an idea, so you never quite get there. You're not Buzz Lightyear. You're not Buzz Lightyear. You can't go to infinity and then beyond. You just got a soft parenthesis on that. All right, so this means this. These mean the same thing. The bracket in interval notation is the same. That means equal to or equal to. The parentheses are like that and that without the not equal to, strict inequalities. Whenever you're doing interval notation, it's always small, comma, large. Small, comma, large. So notice we didn't go 4/3, comma, negative infinity, because that would be backwards. We always start with the smallest or most negative on the left, comma, biggest, most positive on the right. Because what it's doing, what we're doing here, is we're saying like here, 0, 1, 2, 4/3 would be right here. We've got this set. Everything less than or equal to 4/3, right? You can draw it on the line if you want. Yeah, okay. So this is the domain right here. Parenthesis, negative infinity, saying we're not including negative infinity, comma, 4/3, bracket, bracket includes. If we didn't have the or equal to, it would be a parenthesis here. And we never put a bracket on infinity because we can never get to infinity because it's not a number. All right, let's try this one. H of x, we want to find the domain of h of x. For this, we're like, all right, what is this function? It's x plus 1 divided by x squared plus x minus 6. Now here, x plus 1, that's fine. X squared plus x minus 6, that's fine. The not fine part is the fact that we're taking this, we're dividing this, right? We're dividing the x squared plus x minus 6. That's our divisor. It's going into that x plus 1. It's like, oh, rats. What could go wrong with division? Or what number can you not divide by? Can you divide by positive numbers? Like any number divided by positive? Sure. Right? If it's bigger than 1, divide by something bigger than 1, makes it smaller. Divided by some, like a half, makes it twice as big, right? You divide by a negative? Yeah, it's just like dividing by a positive, right? What about a 0? Can we divide by 0? No, we cannot divide by 0, right? And hopefully you already said that, and you just like, listen to me talk. So what we gotta do is say, hey, this rational function has x's or unknowns in the denominator, which means there could be numbers that make this denominator equal 0, and we don't want that. So anytime you have a fraction or a rational expression in a function with a variable in the bottom, in the denominator, you gotta make sure that denominator cannot equal 0. So what we do is we take this x squared plus x minus 6, you take whatever's in the denominator, and you say it cannot equal 0. We write that equals with a slash through it to say it's not equal to 0. And then we're just going to solve this the same way we'd solve if it was equal to 0, except our answer is going to be x cannot equal this or x cannot equal that. Right, we're going to factor this. If you want to use the rectangle, the box diagram can. X squared negative 6, blank plus blank equals 1, blank times blank equals negative 6. Right, we're going to have a 3 and a negative 2. Right, so 3x, negative 2x, x minus 2, x plus 3. Right, maybe you could just look at this probably. X plus 3 times x minus 2. Right, because that multiplies the negative 6, that adds to the 1. Right, because there's a 1 in front of the x squared here. So that is not equal to 0, which means x plus 3 cannot equal 0. X minus 2 cannot equal 0. Take away 3. X cannot equal negative 3. Add 2. X cannot equal 2. So the domain, x cannot equal negative 3. And x cannot equal 2. When we write this, when we say x can't be these two numbers, we're implying it could be anything else. It could be any other number, it could be any real number, except -3 and except +2. If it's -3 or +2, we're going to be dividing by 0, which we cannot do. Any other number here for x other than -3 or 2, we'd be dividing by either a positive or negative number, which we can do. Cool. All right. So, a little recap. If you see a square root, we cannot square root negative numbers when we're dealing with reals. So you take whatever's inside the square root, you got to make it greater than or equal to 0, solve that. Don't forget, if you multiply or divide by a negative, that inequality symbol flips. If you see a rational function, a division, right, fraction, take whatever's in the denominator and make it not equal to 0. Now it's possible you could have something like this, the square root of x plus 1 over 5x minus 3 as your function, g of x, let's say. So here you got two things. You got to make sure this x plus 1 is always greater than or equal to 0, and that 5x minus 3 is not equal to 0. So you'll have to play with that a little bit. That's some fun in the homework. Let's talk domain and range on a graph. So I'm going to sketch a little graph up here. It's not going to be super accurate, but I'm going to do my best. I don't have a projector. So let's say we've got this. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, -5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, -5. Okay. And let's say we're here. And this is just the example out of the textbook. I'm just copying it. So, you know, don't need to reinvent the wheel every time. Let's say we go to 500. All right, but let's do this. So here we got a point at -1, 1. We've got a point at 0, 3. We have a point here at 2, -3. We got a point here at 5, well, let's just say it's 5, 1.5. Doesn't really matter. And we want to know, so first this function just defined here. There's no arrows, right? If I had arrows, then it would say it continues in whatever fashion after the arrow. The textbook doesn't always put arrows after it. If you don't see a dot in the textbook, if it's just like a graph like this, you can just pretend that there's arrows there. If it's like this, then those are endpoints. For some reason, the textbook doesn't use arrows. It should. All right, so let's say we want to find the domain of this function. I want to do that in green. So the domain, this is the x numbers. So say, what are the x numbers here? What's the smallest x number, or the furthest left that this graph goes? Well, it goes to -1 on the left, and then all the way up to 5. If you think about just squishing this graph down, we would get -1 all the way up to 5. But because there's this open dot right here, that means we're not including 5. So the domain is from -1 to 5, and I goofed here. I want you to think, what did I goof on? I goofed because when I'm writing the interval notation, I want to include the -1. So we're going to make a bracket on the -1, and we're going to make a parenthesis on the 5. That means -1 is included in the domain. The smallest x number is -1. 5 is not included because 5 is not actually, x equals 5 is not part of the graph. There's an open dot right there, a hole. But everything in between is included. So that's what this is saying here. All right, let's look at the range now. The range is looking at our y numbers. So this, here we have a continuous function, right? There's no holes or gaps or jumps. I mean, there's a hole right there, but there's, other than that, there's no jumps in there. So For the range, I'm saying, what y numbers do we get? What outputs do we get? What we can do is we can do something similar to what we did for the domain, where we looked at like what x's. We can squish it onto the y-axis and say like, what's the smallest y number? Well, the smallest y number starts down here at -3, and then squish, 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 we get all these numbers, and we go up to +3, all the way up there. Don't worry about this hole right here, because when I push it in, it overlaps twice. Like we get two other outputs that are 1.5. So 1.5 is an output for this graph, or for this function. So here, I go from -3, that's my smallest y number, comma, +3, and there's brackets on either side because I hit both of those values and I get everything in between. Okay. That's domain and range from a graph. If we had something like this, let's say just real quick, and let's say this was at 2, -1, the domain would be all real numbers. Sorry, that's written horribly. It would be all real numbers because we have the arrow going to the left and the arrow going to the right, implying that we're going to get all the x numbers that we want. Right? It's going to keep going to the left, it's going to keep going to the right, get all the real numbers for our x's. The range for this one, for this parabola, the sketch, we get all of these positive y numbers, but the vertex being at 2, -1 means we get all the numbers from -1 and larger. So we'd write -1, comma, infinity, bracket on -1 because we hit -1 as our y number, infinity, parentheses, it just continues going up and up and up and up. But we'll never get there, so we don't put a bracket. Okay. All right, we need to talk a little bit about zeros and x-intercepts. So zeros are just x-intercepts. So if this is our function f, the zeros of f are x equals 1 and x equals 4. So the zeros are basically the same as the x-intercepts. Zeros might just be like x equals, x-intercepts are, right, like 1, 0 and 4, 0. If I ask for a 0, I'm asking for the x-intercept. Basically what I'm trying to say. All right, we need to talk a little bit about increasing, decreasing, and constant, and like what that means for functions. And then we're going to continue using this example here. So increasing, a function is increasing if, as x gets larger, y gets larger. In other words, as we go from left to right on the graph goes up. And I want